Okay, hi everyone. So we worked on implicit differentiation the other day, and let's do an example of that. If I say x squared plus y squared equals to 10, and I ask you to find y prime from here, okay? So there's actually a couple ways of doing it. We could solve for y. Y is equal to the square root of 10 minus x squared. Get rid of the x squared, then square root both sides. That's one way of us doing it. And we can find the derivative of this, which is nice and perfect. And sometimes it might be easier, sure. But the problem with this is that we can't always solve for y. And if we did solve for y, the problem would become a lot weirder. Like if I gave you a problem that said x, y plus y squared equals to 10, and I asked you to solve for y for this problem, there's no way for us to solve for y by itself. Okay? So we want to be able to take the derivative, what we call implicitly, so that we can leave the problem as it is and just deal with it. So I'm going to go ahead and take the derivative of this, which is 2x plus 2y, y prime, equals to 0. Okay. So the idea here, just as a repeat, is that when I take the derivative of x values, that's just what we expect. That's just going to be 1. But when I take a derivative of y, this is just leave it. Or we call it y prime. So when we take the derivative of x squared, first thing we want 2x, derivative of x is 1, and the derivative of y squared is 2y and y prime. Then we go ahead and solve for it, minus 2x to both sides. Oops, that's an x. 2y, y prime equals to negative 2x. Divide both sides by 2y. And we're left with negative x over y. And that is the derivative of our function. Okay. Now, we'll have problems now that aren't as clean-cut as this. And here is an example of this. Let me go ahead and assign this first. Give me a moment. And log problems sometimes start off this way. And when we took the derivative of logs before, let's go ahead and give ourselves an easy example of a log. The derivative of natural log of x is equal to 1 over x, and then you can say x prime, which is just 1. Because chain rule, right? Chain rule. So which is 1 over x. That's what our general rule is. The derivative of log base, let's say 3 of x, was 1 over ln of x. Wait, 1 over x. Let's write it the other way. 1 over ln of 3, x. Let's write it the other way. X natural log 3. That was our rule. And then we take the derivative of x, which is just 1. Okay. We had some other rules for exponentials. So the derivative of e to the x was e to the x. If you want, you can chain rule that, and that is 1. And then the derivative of a to the x was e to the, oh, sorry, it was a to the x ln of a. Oops, I was going to leave lean out there for the whole period again. Okay, so hopefully remember these rules. Now, here is a dilemma that we're going to run into. What if I give you this problem? What is the derivative of x to the x power? Okay. And if you say it's x to the x ln of x, you are completely wrong. And the reason why is the rule I gave you right here, careful here, the rule I gave you here is e and a variable, or are they constants? For instance, this is d over dx, of 3 to the x is equal to 3 to the x ln of 3. But x is a variable, not a constant. So we're going to see a problem that looks like this right now, and we're going to go ahead and try to break it down. Okay? So here's our problem. We'll say y is equal to x to the x power. This is a pretty popular starting problem. And then we say, hey, what is the derivative y prime then? What is the y prime of that? Well, sure, I can take the derivative of y, that's easy. But you can't take the derivative of x to the x power. We actually have no rule for that. There is no rule for that. Again, let's go back and look at it again. The rule that we have works with either e, but e is 2.7, or works for a, where a is some constant. So we actually do not have a rule for doing this derivative. So we have to do some algebra tricks. So the algebra trick is this. Since we don't have a rule for x variable to the variable, what we're going to do is we're going to go ahead and natural log both sides. Because what do natural logs do to exponents? It brings down the gods. So here we go. If I natural log both sides, let me erase this part, get this out of the way. If I natural log both sides, what does natural log do to all exponents? It brings it to the front. Natural log of y equals to x ln of x. And this is actually a trick, you could say. This is the gimmick. You need to know how to solve these variable to the variable exponent. Moving on. Now you can take the derivative of this. Now if you go ahead and take the derivative with respect to x here, on the left side, let's go and take the derivative of natural log of y. We talked about it before. It's 1 over y, and then don't forget the chain rule, y prime. If anyone needs some help figuring out why that's true, please let me know. I can do another example. Okay, the derivative of natural log first, and then you deal with a y on the inside. The derivative of the outside is 1 over y, leave the inside alone, times the derivative of the inside, which is y prime, just to repeat that. Okay, the derivative of x times natural log of x. We need a special rule here. We need product rule. So derivative of the front, leave the back alone, plus the derivative of the back, leave the front alone. To rewrite this, 1 over y prime is equal to natural log of x plus 1. Now, the initial problem asks us to solve for specifically y prime, and we're almost there. So y prime is equal to multiplying y to both sides, y, natural log of x plus 1. We can always rewrite y. Y is x to the x. Y is x to the x. So y prime is equal to x to the x, open parentheses, natural log of x plus 1, then close it. Okay, how do we do there? Okay. Let's do another problem. Let's say y is equal to x to the ln of x. Okay. Our derivative doesn't work with this. Our derivatives work like this: x squared, right? So we use power rule first to bring that down. 2x to the minus 1. 2 minus 1 is 1, and then we multiply by the derivative. So that's power rule. But our power rule doesn't work if there's a variable in the exponent again. So for this problem, we do the exact same thing. We gotta bring down our exponent. So natural log both sides, let's see how that works. Natural log of x to the ln of x. That brings down the exponent to the front. ln of y is equal to natural log of x, natural log of x. Now from here, we can look for y prime. Take the derivative of everyone with respect to dx, or with respect to x. That's 1 over y prime, equals to product rule, 1 over x, ln of x, plus 1 over x, ln of x. So y prime is equal to y, parentheses, natural log of x over x, plus natural log of x over x. And then if you want to rewrite this as y prime is equal to x ln of x, we can leave that alone.
Would you?
Oh, why do we get the?
Making it 2 ln x.
You could do that. 2 ln. Wait. There's a rule. Yeah, that's okay, I think.
Mr. Code, could you repeat why we take the ln of the y and the x at the very top?
Okay, so right here, my problem is this guy here. This is actually not a derivative that we know. It looks like a derivative that we know. It looks like it's e to the x or a to the x, but both of those e and a are both numbers as a base. So this doesn't work because that's a variable at the base. But what about power rule? Power rule has a variable at the base, but it's a constant in the exponent. This is a variable in the exponent. So instead of giving us a constant someplace, it gives us constants nowhere. So what we have to do is we manipulate it so it's not in the exponent position anymore. And then we can use our original tools of how to find derivatives of basic things. Like once I bring down the ln to the front, okay, like here, whoops, let me rewrite that. This becomes, okay, we're at y equals to x ln of x, right? Once I bring this to the front, using natural log, now this is just a product rule problem, no longer a mystery. But originally, it is in a position where I can't even touch it. So.
Wait, Mr. Cole.
Yes.
So after you get the ln of y equals, why do you make it into 1 over y times y prime?
Okay. From this step, we take the derivative to both sides.
Mm-hmm.
And the derivative of natural log y is 1 over y prime. Change.
All right. Mm-hmm.
And then the derivative of ln x is product rule.
All right.
Because the goal, ultimate goal, I should have wrote this, is finding what y prime is. Find that derivative. And sometimes the derivatives look hard to deal with. And maybe it's because we have to first rewrite it. Once we rewrite it, it becomes easier to deal with. I mean, it's still it's ugly, but at least we know some steps to solve it. Go ahead. Was there a question? Okay, let's do another weird one. So y is equal to x to the e to the x. Okay. So natural log of both sides, y, because I'm looking for y prime, I can't take this derivative. This derivative doesn't make any sense to me because we don't have any rules, though it looks like it. It does look like it. It does look like it. But our rules is x squared, which is a constant in the exponent, or that's a 3 to the x, which is a constant in the base. We don't have any ones that have a exponent and an exponent. So when we do natural log, the exponent gets to come down and chill with the rest of us. Brings down the gods. That's how I say it. Natural logs or logs bring down the gods. You could have done this with natural log. It just looks a little bit more messy, but you could have done it.
Wait, why do we put natural log in front again?
Remember, natural log brings down exponents. So if we're saying y is equal to, let's say, 3 to the x, and you don't know how to solve it, we can use natural log. Natural logs or logs. Let's use log base 3 here. Oops, messed that up. So if I log both sides, logs bring down exponents. So we have log base 3 of y equals to x log base 3 of 3. And this cancels out to become 1 log base 3 of y equals to x. Now, some of you guys might know this already, but you could have jumped from this step to this step. Because when you write in log form, it's the base to the exponent equals to your value. 3 to the x equals to y. Circle of logs. Sorry, if you're in my class last year, you kept hearing me sing that over and over and over again. Oh, with auto-tunes. Okay. So this is the reason why logs are super fancy and super helpful when it comes to solving equations, because if the variable's in the exponent, you can't touch it. So till we bring it down, then it's solvable. Variable in the exponent, we can't touch it. It's up on a high shelf.
So why didn't you use ln for that one? Why do you use the log?
You could use, you usually use natural log because it's easier for us. Because the derivative of a log, remember you have to write ln of something. So natural logs are easier to use as a tool. The reason why I use log base 3 here is because this 3 and this 3 would cancel each other out.
All right.
Okay. If I rewritten the problem as y is equal to e to the, let's say, x value here, I would have used natural log because natural log is going to cancel out my e. Goes to the front. Log, whoops, x natural log e, which becomes a 1. Circle of logs.
You really need to make a song in auto-tune.
Do you believe in my path of love? Okay, so now once we're here, this is just a product rule when it makes the problem easier. Again, you enter the problem and you look at this up here and you're like, what the crap? How am I supposed to take this derivative? How am I supposed to take the derivative of that? Variable to the variable power. And the hint, this is the hint, just natural log it to bring it down. And then it becomes a product rule problem. And we can deal with that.
Why does it turn into an e to the x instead of just e times x?
Oh, whoops. I meant this as e to the x power. Sorry. Let me rewrite that.
Okay, makes sense.
I think I just ran into my own mental ceiling. Okay. Now, this becomes a different problem. What if I write x to the g to the x like that? What the hell is that? Can you at least tell me what g is? And the thing is, we don't have to. If we natural log, because this is a variable to the variable, we have to use natural logs to bring down that exponent. Gx natural log of x. And then we take the derivative. The derivative of natural log of y is 1 over y, chain rule, y prime. Now product rule here. Derivative of the front, leave the back alone, plus the derivative of the back, leave the front alone. And that is our setup. We can always say the derivative of something is just g prime. Just stick a prime on it. We'll deal with that later. Okay. And then we can rewrite this as y prime equals to y, and then everything's left over. G prime x ln of x, right? This is just the product rule. And then y could be rewritten as x to the g of x. If you want to plug that back in.
Wait, why do we use g again? Is that just a placeholder?
Yeah, it could be for any function. And the idea is that even if they give you a function in terms of a letter, you can still take the derivative, just call it g prime. And sometimes they might do this because maybe they might give you like a table where they tell you what g is. Okay, let's look at another one. Something kind of weird. Let's do y is equal to, let's do 3 plus x to the x power. Oh, Mr. Code, you can separate the x's, you know? Yeah. No, don't do that. Okay. Remember what this means is you are multiplying 3 plus x, darn it, 3 plus x over and over and over and over as many times as I desire, which would be terrible. Okay. So we do the same thing. I don't know how to take the derivative of this. I don't know. This isn't in my rule book. So I gotta tell you this, the rules that we learned about derivatives pretty much are all the rules that we're gonna use about derivatives. These are all the tools we have on our shelf. If we can't use these tools, we can't find the derivative. So we're gonna try to, Mickey Mouse this as much as we can. So we natural log both sides to bring down the exponent. Okay, now we can take the derivative of this. Like, you can try to bring down the x some other way, but there is no way. You can take the radical of x to both sides. That looks just as ugly. So the gimmick is to know how to use natural logs to bring down those exponents. And then now it's just product rule. 1 natural log of 3 plus x plus the derivative of natural log is 1 over 3 plus x. The derivative of this is just 1. And leave it as x. And then you solve for what they asked me to. If I solve for y prime, solve for y prime. Y natural log of 3 plus x, don't forget the parentheses, plus 1 x over 3 plus x. Close it. And then we can replace this with the original 3 plus x to the x power. So it kind of does look like our initial, like remember this one? E to the x is just e to the x. If I write d over dx of e to the x squared, it's e to the x squared times 2x, chain rule. So this is kind of like that, where you keep your original function, right? Oops. You keep your original y, and then we have some type of leftovers. But that's not an easy derivative. That turned out to be a product rule. Now, if we do this idea, let's try it. Y is equal to e to the x. And let's actually try taking the derivative of this guy, exactly what we just did over here. Natural log to both sides, right? What's the derivative of natural log of e? Oh, sorry. What's the natural log of e? That should just go to 1. Let's take the derivative of this now. 1 over y prime, equals to 1. Y prime equals to y. Y is e to the x. We have just proved our definition for the derivative of e to the x. And we needed to know how to do implicit differentiation to do that. So when we took the derivative of e to the x, we had a rule for that. We proved it just now. Just did it. We might have blinked, but we just did it. Let me try another rule. Let's try another one. Y equals to a to the x, okay? Let's try this rule. So our rule, if we say the derivative rule, the derivative of this is y prime is equal to a to the x ln of a. You guys all cool with that? That's our rule. Straight memorization. But we've been practicing like literally for like last 10 minutes, 20 minutes, no, maybe 10 minutes of, okay, let's pretend I don't know how to do that. That's natural log both sides. Everyone satisfied with that? Okay, bring down the exponent. Now if I take the derivative, it's 1 over y prime equals to, oh, that's not product rule, that's constant multiple. So that's just ln of a. Because what's the derivative of x? Just 1. We move it back, y prime is equal to y, ln of a. Hey, we know what y is. We have just proved the rule we've been working with. You're welcome. Okay, so there's another problem on IXL. I'm just going through questions on IXL here. So if you, okay, well, FY, that's just the rule, right? That's our straight definition. And you could go through the process that we just learned, right, using natural logs to bring down exponents. And we ended up with our definitions when we first learned them like 3 weeks ago. Now, okay, got one more for you. This is our last one, I think. Y is equal to bracket natural log of x to the bracket of x power. Okay. Okay, we natural log both sides. X ln of x, right? And then we take the derivative of this. The derivative of natural log is 1 over y prime. And we do product rule here. X ln of x, leave the back alone, plus the derivative of the back. Now this is going to be hard. This is going to be crazy, okay? So since this is an onion, right, layer inside a layer inside a layer, let's do the outside layer first. It's 1 over natural log of x, because we're just copying the inside. The outside layer is done. Chain rule times the derivative of this guy, which is 1 over x, times the derivative of x, which is 1, times, leave the front alone. Okay, let me go ahead and link that again, so you guys can see. This derivative is this whole section here, followed by this derivative here, which is this section here, followed by chain rule one more time, which is this section here. And then y prime is equal to y, and then all this stuff. Natural log x, oops, I forgot the x,
Wouldn't
plus,
there be no x? Because you take the derivative of the first part, and that's just 1.
Oh, yeah, you're right. I messed up. I just copied it. That should be a 1. Thank you. Thanks for catching that.
Yeah.
I'll leave a ghostly shadow. That was a 1. And then this is 1 over, oh, there's x that cancels out, right? 1 over natural log x. And then y, you can rewrite that y as this guy here if you really want to. Okay. All right, that's it. Anyone have any questions? I'm sorry, I should have read the chat. Uh-oh. Thanks for letting me know, Crystal. Okay, I think that's it for us, for example-wise. Thanks.